Have you ever wondered how stone can look like living creatures, how caves can hold forests, or how ice can reach into the sea? Tonight on Unearthed Secrets, we journey from whale-shaped rocks and glowing caves to hidden worlds beneath mountains, collapsed volcanoes, and ice that moves like land. Before we begin, please like, subscribe, and share where you're watching from, and what time it is for you right now. The stones that surfaced from time. In northeastern Thailand, far from the country's crowded beaches and modern skylines, three immense stone forms rise quietly above the forest canopy. From certain angles, they resemble the backs of whales, breaking the surface of a green ocean. From others, they appear as weathered hills, shaped by slow hands rather than sudden force. Known as Hin Sam Wan, or Three Whale Rock, these formations sit high above the Mekong River Basin in Bueng Kan Province, forming one of Southeast Asia's most striking yet understated natural megastructures. Unlike cliffs that confront the sea or towers that pierce the sky, Hin Sam Wan reveals itself gradually. The landscape here does not announce danger or drama. Instead, it invites patience. The rocks are massive, but their presence is subtle, a reminder that some of Earth's greatest structures do not overwhelm through height or violence, but through endurance. The story of Hin Sam Wan begins deep in geological time, long before Thailand existed as a recognizable landmass. The rocks that form the three whale formations are composed primarily of sandstone, laid down during the late Jurassic to early Cretaceous periods, approximately 140 million years ago. At that time, this region was not forested highland, but part of a vast river system, where sand, silt, and sediment accumulated slowly in floodplains and shallow basins. Layer by layer, these sediments compacted under pressure, cemented by minerals carried by groundwater. Over millions of years, they hardened into thick sandstone beds. Unlike limestone, which dissolves chemically, sandstone erodes primarily through physical processes: wind abrasion, water runoff, temperature changes, and gravity. Tectonic forces later uplifted the region, raising these ancient sedimentary layers above surrounding terrain. As rivers cut downward and surrounding rock eroded away, more resistant sections of sandstone remained. Hin Sam Wan represents such remnants, stone masses that survived while adjacent material disappeared. What makes the three whale rock distinctive is not only its size, but its shape. Each of the three formations curves smoothly, with rounded backs and sloping flanks. These shapes are not accidental. They are the result of exfoliation weathering, a process common in massive rock formations. As pressure on buried rock is released through erosion, outer layers peel away in curved sheets, rounding the surface over time. This slow peeling creates dome forms rather than jagged peaks. Over tens of millions of years, repeated cycles of heating, cooling, wetting, and drying smooth the rock into the whale-like shapes seen today. From above, the formations align in a sequence: the father, mother, and child whales, as described in local tradition. The largest formation leads, followed by two smaller ones, as if moving together through time. This alignment reinforces the visual metaphor that gave the site its name. Yet Hin Sam Wan is not merely a visual curiosity. It is part of a larger sandstone plateau that stretches across northeastern Thailand and into Laos. Similar rock forms exist throughout the region, but few are as exposed or as clearly defined as these three. For centuries, the area remained largely unknown outside local communities. Dense forest, limited access, and lack of development kept the site isolated. The rocks were familiar to villagers, hunters, and monks, but not to tourists. This isolation preserved the landscape's integrity far longer than many natural landmarks elsewhere. Local folklore surrounds the three whale rock. One story tells of ancient whales that swam inland during a great flood, becoming stranded and turning to stone as the waters receded. Another interprets the formations as guardians, watching over the Mekong River and the land beyond. These stories do not attempt to explain geology. They explain relationship, how people understand massive, silent presences in their environment. Such interpretations are common across cultures. When stone takes organic form, humans instinctively assign life to it. Hin Sam Wan's resemblance to living creatures bridges gap between geology and imagination, making it easier to relate to a structure that predates humanity by more than 100 million years. From scientific perspective, the The site offers valuable insight into erosional stability. Despite exposure, the rocks have remained intact for immense spans of time. Their rounded shapes help deflect water, reducing concentrated erosion. Vegetation on surrounding slopes stabilizes soil and moderates runoff. Together, these factors have allowed the formations to persist, while nearby terrain changed dramatically. The forest surrounding Hin Sam Wan plays a critical role. Tree roots anchor soil, slowing erosion. Leaf litter absorbs rainfall. Shade reduces temperature extremes on rock surfaces. The relationship between stone and forest is symbiotic. The rock supports forest by shaping terrain. The forest protects the rock by regulating erosion. This balance is fragile. In recent years, Hin Sam Wan has gained attention through photography and social media. Images of the whales at sunrise and sunset spread quickly, drawing visitors eager to see the formations for themselves. Access roads were improved. Viewing platforms were installed. The site transitioned rapidly from obscurity to prominence. With the visibility came new challenges. Foot traffic compacts soil. Unregulated paths increase runoff. Litter threatens fragile ecosystems. Authorities now face the same dilemma seen worldwide: how to share a natural landmark without accelerating its degradation. Management efforts focus on controlled access, designated trails, and education. Visitors are encouraged to view the rocks from specific points rather than climbing on them. This is crucial because sandstone, though durable, fractures under repeated stress. Human weight, combined with moisture and temperature variation, can accelerate exfoliation and cracking. From the viewing areas, the landscape opens dramatically. The forest stretches to horizon. On clear days, the Mekong River basin is visible in the distance. The rocks rise gently above canopy, not towering, but unmistakable. Their size becomes apparent through comparison. Trees appear small, trails narrow, people reduced to dots. The experience is quiet. Unlike coastal cliffs where waves roar, or karst towers where echoes dominate, Hin Sam Wan is defined by stillness. Wind moves through trees. Insects hum. Birds call. The rocks themselves are silent. This silence emphasizes the scale of time involved. These formations have endured tropical storms, monsoon cycles, climate shifts, and biological change far beyond human memory. They have witnessed forests advance and retreat, rivers change course, species appear and vanish. Geologically, Hin Sam Wan continues to change, though slowly. Rainwater flows along shallow grooves, widening them grain by grain. Small flakes detach from the surface. Lichens colonize cracks, accelerating micro-weathering. These processes are subtle but constant. Over thousands of years, the shapes will evolve further. Edges will soften, surfaces will recede. Eventually, the formations will lose their recognizable whale-like form, blending back into the broader plateau. This is not destruction. It is continuation. From cultural standpoint, the site has become symbol of Buen province, a marker of regional identity. It represents connection between land and story, between deep time and present awareness. But this symbolism brings responsibility. Preserving meaning requires preserving form, at least long enough for future generations to understand it. Hin Sam Wan also contributes to broader scientific understanding of sandstone landforms in tropical environments. Most well-known sandstone features are studied in arid regions, where erosion is dominated by wind. Here, water is primary agent. Comparing these systems helps geologists model landscape evolution under different climates. Unlike karst landscapes, which dissolve internally, sandstone landscapes like Hin Sam Wan erode externally. This makes their forms more rounded, less cavernous, and often more stable in short term. But they are not immune to collapse. Internal fractures, if widened enough, can lead to sudden failure. For now, the three-well rock remains intact. At sunrise, light moves across the curved backs of the formations, highlighting their smooth contours. Mist rises from forest below, enhancing illusion of whales surfacing. At sunset, shadows stretch long across the plateau, emphasizing mass and curvature. At night, stars hang above, and the rocks become dark silhouettes once more. These daily cycles reinforce the site's character. Hin Sam Wan does not demand attention. It rewards observation. In a world increasingly dominated by spectacle, the three-well rock offers different lesson. It shows that geological significance does not require height, drama, or danger. It requires time. It requires patience. It requires restraint. The formations are reminders that Earth's greatest structures are often those that endure quietly, shaping and being shaped without announcement. They are not monuments of conquest. They are survivors of subtraction. Hin Sam Wan exists because surrounding rock disappeared, because erosion chose elsewhere, because time moved unevenly. The whales did not rise suddenly. They were revealed. And as long as forest stands, water flows gently, and human presence remains respectful, they will continue to surface from time, silent, massive, and unchanged within the span of human lives. The Three Whale Rock is not spectacle carved for visitors. It is a record of endurance written in sandstone, a reminder that the earth doesn't rush, and that its greatest stories are told slowly. The canyon carved by light. In the high desert of northern Arizona, where the land appears dry, open, and unbroken, a narrow opening in the ground leads into one of the most visually arresting landscapes on Earth. There are no towering peaks announcing its presence, no distant silhouettes hinting at what lies below. Antelope Canyon reveals itself only when one steps inside. What appears from above as a thin crack in sandstone opens into a winding corridor of sculpted stone, shaped not by sudden force, but by repetition. Water moving through rock, again and again, over immense spans of time. Antelope Canyon lies within the Navajo Nation, just east of Page, Arizona, carved into the Navajo sandstone, a rock formation deposited approximately 190 million years ago during the early Jurassic period. At that time, this region was not desert, but part of one of the largest sand dune systems ever to exist on Earth. Wind-driven dunes piled sand into thick layers, compacted over time into sandstone with distinct cross-bedding patterns still visible today. This sandstone is both strong and fragile. It can support smooth flowing walls, yet it fractures easily when water finds a weakness. Antelope Canyon exists because water repeatedly found such weaknesses. The canyon is classified as a slot canyon, a type of narrow passage carved almost entirely by water erosion. Unlike broad canyons shaped by rivers over long periods, slot canyons form when sudden, high-energy floods rush through narrow openings. These floods may last only minutes or hours, but their force is concentrated, capable of removing large volumes of sand and rock in a single event. Antelope Canyon's shape is the result of thousands of such floods. Rainfall far upstream funnels into shallow washes, which converge toward the canyon. When intense storms occur, often many kilometers away, water surges through the slot without warning. Sand carried by floodwater acts as an abrasive tool, grinding the sandstone walls smooth, rounding edges, and deepening the canyon. Each flood modifies the canyon slightly. One removes material from the base, another smooths a curve, another undercuts a wall. Over tens of thousands of years, these small changes accumulated into the flowing sculptural forms visible today. Antelope Canyon is divided into two main sections, Upper Antelope Canyon and Lower Antelope Canyon. Though close geographically, they differ in form, accessibility, and behavior. Upper Antelope Canyon, known in Navajo as Tse Biganilini, the place where water runs through rocks, is wider at ground level and shallower in depth. Its floor is relatively flat, allowing easier access. This section is famous for beams of sunlight that penetrate narrow openings above, illuminating dust particles and creating shafts of light that appear solid in photographs. Lower Antelope Canyon, or Hasdistazi, spiral rock arches, is deeper, narrower, and more complex. It requires ladders and stairs to navigate, and its walls twist more tightly. Floodwaters here move faster, carving more aggressive curves and sharper turns. Despite their differences, both sections share the same fundamental origin: flash flooding. This makes Antelope Canyon inherently dangerous. Water can rise several meters within minutes. Because the canyon is narrow, there's nowhere to escape once flooding begins. In 1997, a sudden flash flood claimed multiple lives in Lower Antelope Canyon, underscoring the ongoing risk. Since then, access has been carefully regulated, and weather conditions are monitored closely. This danger is not anomaly. It is the same process that created the canyon in the first place. The canyon's walls display remarkable textures. Smooth, wave-like forms alternate with ridges and hollows. These shapes reflect variations in sandstone hardness, grain size, and cementation. Where rock was slightly softer, erosion proceeded faster. Where it was harder, curves tightened rather than collapsing. Color plays a critical role in perception. The Navajo sandstone contains iron oxides that stain the rock in shades of red, orange, pink, and purple. As sunlight enters the canyon, it reflects off walls repeatedly, intensifying color and creating gradients that shift minute by minute. Light is as much a sculptor here as water. Though it does not erode rock directly, it defines how the canyon is experienced. At certain times of day, sunlight enters at steep angles, bouncing between walls and illuminating surfaces that would otherwise remain dark. This reflected light softens shadows, emphasizing curves and making stone appear fluid. The famous light beams occur when sunlight passes through narrow openings overhead and reflects off airborne dust. These beams are not constant. They depend on season, sun angle, and atmospheric conditions. When they appear, they transform the canyon into a space where light feels tangible. But even without beams, the canyon remains dynamic. As clouds pass overhead, colors shift. As the sun moves, highlights slide along walls. The canyon never looks the same twice. From a geological perspective, Antelope Canyon is relatively young. Compared to massive cliffs or karst towers formed over hundreds of millions of years, this slot canyon likely developed over tens of thousands of years. Perhaps less. Its rapid formation highlights how concentrated energy can reshape landscapes quickly under the right conditions. This does not mean the canyon is stable. Erosion continues today. Every flood removes more material. Walls thin, floors deepen, some sections widen. Others collapse slightly and are reshaped by subsequent floods. The canyon's beauty depends on this ongoing change. Human presence in the region long predates modern tourism. The Navajo people have lived in and around this land for generations. To them, Antelope Canyon is not just a geological feature, but part of cultural landscape. It is respected as a place shaped by natural forces that demand humility. Traditional knowledge recognizes the danger of slot canyons. Stories emphasize respect for weather, water, and terrain. This understanding aligns closely with geological reality. The canyon is safe only under specific conditions, and those conditions can change rapidly. Modern access to Antelope Canyon is entirely guided and regulated by the Navajo Nation. This is not only for safety, but for preservation. Foot traffic, touching walls, and debris can alter delicate surfaces. Sandstone erodes easily under repeated contact. Photography has played a major role in the canyon's global fame. Images of flowing sandstone and light beams spread rapidly, turning Antelope Canyon into one of the most photographed natural spaces in the world. This visibility increased pressure on the site, making management essential. Today, group sizes are controlled. Paths are designated. Entry is restricted during rain forecasts. These measures aim to balance access with protection. Ecologically, the canyon supports limited but specialized life. Mosses and lichens cling to shaded walls. Small plants grow near openings where light reaches. Animals pass through occasionally, but the canyon is not habitat in traditional sense. Its value lies more in geology and hydrology than biodiversity. Water behavior within the canyon is studied closely. Hydrologists analyze flow patterns to predict flood risks and understand erosion rates. The canyon functions as a natural laboratory for studying extreme erosion in confined spaces. The surrounding desert, though dry, contributes significantly. Sparse vegetation allows rain to run off quickly rather than being absorbed, increasing flood intensity. Climate change may alter rainfall patterns, potentially increasing frequency or severity of flash floods. This possibility raises questions about the canyon's future. More intense storms could accelerate erosion, widening or deepening sections rapidly. Alternatively, collapse of certain areas could change access or eliminate iconic features entirely. As with many natural landmarks, there's no plan to preserve Antelope Canyon in a fixed state. Its meaning comes from motion and change. To freeze it would be to destroy what created it. The experience of moving through the canyon is unlike any other landscape. The sky is reduced to thin ribbon overhead. Sound behaves strangely, echoing softly. Temperature remains cooler inside, shielded from desert sun. One's sense of scale shifts. Walls feel close, yet immense. The canyon compresses attention. Distractions fade, movement slows. Visitors often fall silent, guided more by environment than instruction. This psychological effect is common in slot canyons. The confined space heightens awareness of surroundings. It is easy to forget time, easy to forget the desert above. And yet, above is where danger comes from. This duality defines Antelope Canyon. It is tranquil and violent, delicate and powerful, ancient and young. It exists because of water, yet water threatens it constantly. Every curve tells story of floodwater that passed through. Every smooth wall marks sand carried at speed. Every narrowing reflects resistance. Every widening surrender. Antelope Canyon is not monument to endurance. It is record of repetition. Water does not carve it once. It carves it again and again. The canyon's beauty lies in this repetition, in how consistent forces produce graceful results over time. Standing within its walls, one is reminded that landscapes need not be vast to be powerful. Antelope Canyon is narrow, hidden, and temporary. But within that narrow space, it reveals more about Earth's processes than many grander features. It shows how quickly land can change, how fragile rock can be, how light transforms stone, and how time works not only in millions of years, but in moments of sudden force. Antelope Canyon will continue to evolve. Its curves will shift. Its walls will smooth further. Some passages may close. Others may open. The canyon is not finished. It is still being written. And as long as rain falls on desert sands above, as long as water finds its way into cracks, Antelope Canyon will remain what it has always been. A place where stone yields to motion and where the hidden work of erosion becomes visible. The caves that became a night sky. Beneath the gentle hills and farmland of New Zealand's North Island lies a hidden world shaped by water, time, and life itself. From the surface, the Waitomo region appears calm and ordinary. Rolling green fields, limestone outcrops, quiet rivers. Nothing suggests that below the ground exists a vast underground system where darkness is pierced by thousands of living lights, transforming stone chambers into something resembling a night sky. This is the Waitomo Glowworm Caves, one of the most unusual natural environments on Earth. The origins of the Waitomo Caves stretch back around 30 million years, to a time when much of New Zealand lay submerged beneath warm, shallow seas. Marine organisms thrived in these waters: shellfish, corals, microscopic plankton. And when they died, their calcium-rich remains settled on the seabed. Over millions of years, these layers compacted into limestone, forming thick deposits beneath the ocean floor. Later, tectonic forces lifted this limestone above sea level, as the New Zealand landmass slowly emerged. Once exposed, the rock became vulnerable to one of the most powerful geological forces on Earth: water. Rainwater absorbed carbon dioxide from the air and soil, forming a weak acid capable of dissolving limestone. As rain seeped into cracks and joints, it slowly widened them, creating underground voids that expanded over immense spans of time. This process, known as karst erosion, produced the Waitomo Cave system. Unlike caves carved by lava or ice, Waitomo's passages were shaped almost entirely by flowing water. Underground rivers carved tunnels, altered their courses, and left behind chambers as water levels shifted. Some passages remain active waterways today, while others are dry remnants of earlier phases. Inside the caves, the evidence of this long history is everywhere. Smooth walls mark ancient river channels. Vertical shafts indicate places where water once poured downward. Stalactites hang from ceilings where mineral-rich water drips slowly, depositing tiny layers of calcite. Stalagmites rise from floors where droplets fell repeatedly in the same place. These formations grow extremely slowly, often less than a millimeter per year, meaning many visible structures took tens of thousands of years to form. Long before humans entered the caves, they were already dynamic systems. Water flowed, ceilings collapsed, minerals accumulated, and life began to adapt to the darkness. The Waitomo Caves have been known to the Maori people for centuries. The name Waitomo comes from the Maori words wai, meaning water, and tomo, meaning hole or passage, water entering the ground. Maori oral history describes knowledge of the caves long before European contact, and they were used for shelter, burial, and spiritual purposes. Some caves were considered sacred, places connected to the underworld and ancestral realms. European exploration began in the late 19th century. In 1887, Maori chief Tanetino Rao guided surveyor Fred Mace into the caves using candles and a small raft. As they drifted through a dark chamber, they noticed hundreds of small blue-green lights glowing above them. This chamber would later become the most famous part of the cave system, the glowworm grotto. What they had discovered was not a mineral phenomenon, but a biological one. The glowworms of Waitomo are the larvae of a species called Arachnocampa luminosa, found only in New Zealand. Despite their name, they are not worms at all, but the juvenile stage of a fungus gnat. Their glowing ability is a survival adaptation, not a decorative feature. Glowworm larvae live attached to cave ceilings. From their bodies, they produce fine silk threads coated with sticky droplets. These threads hang down like fishing lines. The glowworm emits light from a specialized organ in its tail, attracting flying insects drawn toward the glow. When an insect becomes trapped in the sticky threads, the larva reels it in and feeds. The light itself is produced through a biochemical reaction similar to that seen in fireflies. Oxygen reacts with a compound called luciferin, catalyzed by an enzyme known as luciferase, producing light without heat. This process is highly efficient and allows the glowworms to shine continuously for long periods. The intensity of the glow varies depending on conditions. Glowworms shine brightest when hungry. When food is abundant, the glow dims. Humidity, temperature, and air movement also affect brightness. In dry conditions, glowworms may reduce activity or die, making stable cave environments essential for their survival. The caves provide exactly what glowworms need: constant humidity, darkness, and a steady supply of insects carried in by air currents and water. Over time, the cave ecosystem evolved around this delicate balance. The glowworm grotto itself is a large chamber with a high ceiling, formed when part of the cave roof collapsed long ago. The chamber opens into an underground river, and it is here that visitors often drift silently by boat, looking upward as thousands of glowworms create the illusion of a star-filled sky. What makes this experience unique is not just the presence of light, but the contrast. The surrounding darkness is complete. There are no reflections, no external illumination. The glowworms become the only reference points, creating a sensation of floating beneath a living galaxy. But this beauty masks fragility. Glowworms are extremely sensitive to environmental change. Artificial light disrupts their behavior. Touching cave walls can alter humidity. Carbon dioxide from large groups of visitors can affect air quality. Changes in water flow can destroy larvae colonies. Because of this, human access to the caves is carefully managed. Modern tourism at Waitomo is regulated to preserve the ecosystem. Boats move silently. Photography is restricted. Lighting is kept minimal. Visitor numbers are controlled. These measures aim to protect the glowworms while allowing people to experience the caves responsibly. Beyond the glowworms, the Waitomo cave system contains a complex network of passages, some open to visitors and others accessible only to researchers and experienced cavers. Underground rivers continue to carve new routes, especially during heavy rainfall when water levels rise dramatically. Flooding remains one of the greatest natural forces shaping the caves today. During intense storms, water rushes through narrow passages, transporting sediment and debris. These flood events can alter cave floors, widen tunnels, and sometimes destroy delicate formations. The same process that created the caves continues to reshape them. Ecologically, the caves host more than just glowworms. Cave weta, blind insects, bacteria, and fungi form a specialized ecosystem adapted to darkness. Nutrients enter primarily through water and organic material washed in from above. Every organism in the cave depends on this limited input, making the system highly interconnected. Scientists study the Waitomo caves to better understand karst hydrology, cave ecosystems, and bioluminescence. Research on Arachnocampa luminosa has contributed to broader understanding of biological light production and insect behavior. The caves also provide insight into climate history, as stalactites preserve chemical records of past rainfall and temperature conditions. From a geological perspective, the caves demonstrate how quickly landscapes can change beneath the surface. While hills above appear stable, underground spaces expand, collapse, and reroute water continuously. What looks permanent on the surface may be hollow below. The cultural significance of Waitomo continues today. Maori involvement in cave management remains central, and the caves are seen not only as natural attractions, but as taonga, treasures that carry ancestral meaning. This perspective emphasizes guardianship rather than ownership, aligning closely with conservation goals. Experiencing the glowworm caves often leaves visitors quiet and reflective. The darkness, the slow movement of water, and the gentle glow overhead create an atmosphere that feels removed from time. There's no sense of scale in the usual way. The ceiling disappears into blackness. The glow appears infinite. This effect is not accidental. It is the result of millions of years of geological shaping, combined with thousands of years of biological adaptation. The caves are not designed for spectacle. They became remarkable by accident, yet they are not static. Glowworm populations rise and fall. Floods reshape passages. Stalactites continue to grow or break. The caves remain alive in geological and biological terms. Even the glowworms themselves are temporary, living only months in larval stage before emerging as short-lived adult gnats. The Waitomo glowworm caves are therefore not monuments of stone alone. They are living systems, places where geology, biology, water, and time intersect continuously. They remind us that the most extraordinary landscapes are sometimes hidden, that light can exist without fire, that beauty can depend on darkness, and that even beneath the most peaceful countryside, the earth is constantly at work. The caves did not form to be seen. The glowworms did not evolve to be admired. Yet together, they created something unforgettable. In Waitomo, the night sky does not belong to the heavens. It belongs to the earth itself, glowing quietly beneath our feet. The cave that holds its own world. Deep within the remote forests of central Vietnam lies a cavern so vast that it alters weather, creates forests, and contains rivers that vanish into darkness. This is San Dung Cave, the largest known cave on Earth by volume. A subterranean world hidden beneath the limestone mountains of Phang Nakabang National Park. Unlike caves defined by narrow passages or decorative formations, San Dung is defined by scale. It is not simply entered, it is descended into, crossed, and endured. From above ground, there is little indication of what lies below. The jungle canopy stretches uninterrupted across karst hills, concealing fractures and sinkholes that open into enormous voids beneath the surface. San Dung remained undiscovered by science until the late 20th century, not because it was inaccessible, but because its entrance was easy to miss. A yawning opening swallowed by forest and mist, breathing air from the depths below. The geological story of San Dung begins over 400 million years ago, when much of what is now central Vietnam lay beneath a warm, shallow sea. Over immense spans of time, marine organisms lived and died, their calcium-rich shells settling on the seabed. These sediments compacted into thick layers of limestone, forming the foundation of the Annamite mountain range. As tectonic forces uplifted the region, the limestone rose above sea level and fractured. Rainwater, absorbing carbon dioxide from air and soil, became weakly acidic and began dissolving the limestone along joints and faults. This process, karstification, carved underground pathways as water flowed downward and sideways through the rock. Unlike many caves formed by slow dripping or minor streams, San Dung was shaped by a powerful underground river. Over millions of years, this river cut an enormous tunnel through the limestone, enlarging fractures into chambers of extraordinary scale. Sections of the cave collapsed as ceilings weakened, creating massive voids and allowing sunlight to penetrate deep underground. San Dung is estimated to be more than 9 kilometers long, with chambers reaching 200 meters in height and 150 meters in width, large enough to contain skyscrapers. In some areas, clouds form inside the cave due to temperature differences between interior and exterior air. Few places on Earth blur the line between surface and subterranean environments so completely. Despite its scale, San Dung remained unknown to the modern world until 1990, when a local man named Ho Kan encountered a large opening while sheltering from a storm in the forest. He felt wind rushing from the entrance and heard the sound of water far below. Unable to descend and unaware of its significance, he left the site behind. For years, its location was forgotten. It was not until 2018 that British carvers, led by Howard Limbert, rediscovered and surveyed San Dung with Ho Kan's guidance. What they found exceeded expectations. Measurements confirmed that San Dung surpassed all known caves in size. The discovery reshaped understanding of cave formation limits and placed Vietnam at the center of speleological research. Entering Sandung is not a casual act. Access requires days of trekking through dense jungle, river crossings, and steep descents. There are no artificial walkways, no lighting systems, no permanent structures inside. The cave remains largely untouched, its environment preserved through strict access control. Inside, the cave reveals layers of geological history. Towering walls display horizontal bedding planes, ancient seabeds stacked vertically. Massive stalagmites rise more than 70 meters, formed where mineral-rich water dripped over tens of thousands of years. Flowstone cascades down walls like frozen waterfalls. These formations are not decorative. They are structural records of water movement and chemical deposition. One of Sundung's most remarkable features is its collapsed ceiling sections, known as dolines or skylights. Through these openings, sunlight pours into the cave, allowing vegetation to grow far underground. In one chamber, a full jungle thrives, complete with trees, vines, mosses, and insects. This area is often called the Garden of Eden, though it is not a metaphor. It is a functioning ecosystem isolated within a cave. These skylight forests exist because collapse opened the cave to surface conditions. Rain enters directly. Seeds are carried by wind, birds, and water. Over time, soil accumulated on fallen rock. Plants rooted. A microclimate developed. This environment differs sharply from surrounding jungle. Shaped by limited light and enclosed space, Sundung also contains its own weather system. Warm, humid air inside the cave rises toward openings, drawing in cooler air from entrances. This circulation can generate mist and low clouds within chambers. Condensation forms on walls. Dripping water echoes constantly. The cave breathes. Water remains central to Sandung's evolution. An underground river still flows through parts of the cave, disappearing into siphons and re-emerging downstream. During heavy rains, water levels can rise dramatically, reshaping sediment banks and altering passage routes. Flooding is a natural and ongoing force here, continuing the cave's formation. Biologically, Sandung hosts species adapted to darkness and isolation. Cave-dwelling insects, spiders, and fish exhibit reduced pigmentation and eyesight. Some species are endemic, found nowhere else on Earth. In skylight zones, surface species mingle with cave organisms, creating unusual overlaps. Scientists study Sandung to understand karst hydrology, cave climatology, and ecosystem development in extreme environments. The cave provides rare opportunity to observe how life colonizes newly exposed underground spaces and how large caves evolve structurally over time. Human impact inside Sandung is deliberately minimal. Tourism is tightly regulated, with a limited number of guided expeditions allowed each year. Campsites are temporary. Waste is removed. No permanent installations are permitted. These measures aim to prevent damage to formations that took hundreds of thousands of years to form. This approach reflects recognition that Sandung is not a spectacle to be consumed, but a system to be respected. Even small disturbances, touching formations, altering airflow, introducing contaminants, could have lasting effects. For those who enter, the experience is often overwhelming. Scale is difficult to comprehend. Sound behaves differently. Light disappears and reappears unpredictably. Time feels distorted. Walking across cave floors takes hours, not minutes. The sense of isolation is profound. Sandung challenges assumptions about what caves are. It is not narrow, claustrophobic, or decorative. It is open, vast, and raw. It resembles an underground valley more than a tunnel. In places, it feels like standing inside a mountain hollowed from within. Geologically, Sundung demonstrates that cave size is limited not by imagination, but by conditions. Given sufficient water flow, soluble rock, time, and structural stability, subterranean spaces can rival surface landscapes in scale. The cave also serves as a reminder that much of Earth remains unexplored. Despite satellites, mapping, and technology, entire worlds can exist unnoticed beneath familiar terrain. Sandung was not hidden by secrecy, but by assumption. Few believed such a cave could exist. The surrounding Phang Nakebang region contains hundreds of other caves, many still unexplored. Sandung may not remain unique forever, but its discovery shifted the upper boundary of what is considered possible underground. Over geological time, Sandung will continue to change. Ceilings will collapse further, skylights may widen, rivers will carve new routes, forests may expand or vanish. Eventually, the cave may open fully to the surface, becoming a canyon rather than a cavern. This is not failure, it is progression. Sandung exists at a particular moment in Earth's long story, large enough to astonish, stable enough to persist, but temporary in geological terms. Its immensity does not make it permanent. Standing inside Sandung, one is reminded that the planet builds and dismantles on its own schedule. Mountains rise and hollow, rivers disappear underground, forests grow in darkness, and human presence remains brief. Sandung is not merely the largest cave in the world. It is a measure of patience, a record of water's persistence, a reminder that Earth's greatest structures are sometimes hidden from view. It holds its own sky, its own weather, its own life, and it does so quietly, beneath a forest that gives no hint of what lies below. The crater that became a world. In northern Tanzania, where the East African highlands rise in long volcanic ridges and grassy plains stretch toward the horizon, there exists a vast natural enclosure, unlike any other on Earth. From above, it appears as a perfect ring, a colossal bowl carved into the land, enclosing rivers, forests, lakes, and tens of thousands of animals within its walls. This is Ngorongoro Crater, the largest intact volcanic caldera on the planet, and one of the most complex natural systems ever formed by geological collapse. Ngorongoro is not simply a crater, it is a contained world, a place where geology, climate, wildlife, and human history intersect within a single, clearly defined boundary. Unlike valleys shaped by erosion or basins carved by water, Ngorongoro exists because a mountain destroyed itself. The story begins more than 2.5 million years ago, during a period of intense volcanic activity along the East African Rift System. At that time, Ngorongoro was not a crater at all, but a massive volcano, possibly taller than Mount Kilimanjaro is today. It rose thousands of meters above the surrounding plains, fed by magma rising through fractures in Earth's crust as the African continent slowly pulled itself apart. For hundreds of thousands of years, the volcano erupted repeatedly, building layer upon layer of lava, ash, and volcanic debris. Then, at the height of its growth, the system failed. The magma chamber beneath the volcano emptied rapidly. No longer able to support the immense weight above it, the mountain collapsed inward, imploding rather than exploding. What remained was a caldera approximately 19 kilometers wide, with walls rising up to 600 meters high. Unlike many volcanic craters that erode or fracture over time, Ngorongoro's rim remained remarkably intact. Rainfall was sufficient to support vegetation, but not so extreme as to destroy the structure. The result was a natural enclosure, vast, fertile, and largely sealed. Over time, water collected at the crater floor. Seasonal rivers flowed down the walls. Lakes formed and receded. Volcanic soils enriched the land, creating one of the most productive ecosystems in Africa. While surrounding landscapes changed with climate cycles, Ngorongoro became a refuge. The crater floor covers roughly 260 square kilometers and contains a mosaic of habitats. Open grasslands dominate much of the basin, supporting grazing animals. Acacia woodlands occupy sheltered areas near the rim. Swamps fed by underground springs remain green even during dry seasons. At the center lies Lake Magadi, a shallow alkaline lake that expands and contracts with rainfall. This diversity exists within a space that can be crossed in hours, yet supports extraordinary biological density. Ngorongoro is home to an estimated 25,000 to 30,000 large mammals, including wildebeest, zebra, buffalo, gazelle, elephants, lions, hyenas, cheetahs, and one of the densest populations of spotted hyenas anywhere on Earth. It is also one of the few places where critically endangered black rhinoceros still survive in relative safety. What makes this possible is containment. While animals are free to move within the crater, relatively few leave. The steep walls act as natural barrier, limiting migration. As a result, predator and prey populations coexist year-round, creating unusually stable ecological dynamics. This stability is rare in Africa, where most ecosystems depend on large-scale seasonal migrations. In Ngorongoro, the land itself provides continuity. Grass grows year-round due to groundwater and mineral-rich soils. Springs fed by volcanic aquifers sustain swamps even in droughts. This allows herbivores to remain and predators to follow. The predator-prey relationships here are intense and constant. Lions hunt daily. Hyenas patrol continuously. Scavengers such as vultures circle overhead. With limited space, competition is fierce, yet the system persists, balanced through numbers and behavior rather than movement. Elephants in Ngorongoro are notable for their size. Many bulls develop exceptionally large tusks, a result of older age structures and reduced poaching pressure. These elephants shape the crater's vegetation, breaking trees and opening woodlands, influencing where other species can thrive. Bird life is equally diverse. More than 500 bird species have been recorded in and around the crater. Flamingos gather at Lake Magadi when water levels allow. Raptors soar along the rim. Waterfowl inhabit marshes. The crater functions as both habitat and crossroads. But Ngorongoro is not untouched wilderness. Humans have been part of this landscape for millions of years. Just outside the crater lies Olduvai Gorge, one of the most important paleoanthropological sites on Earth. Fossils found there document early human ancestors dating back nearly 2 million years, including Homo habilis and Homo erectus. Stone tools scattered through sediment layers record the gradual development of human technology. These early hominins likely used the Ngorongoro highlands as resource-rich environment, hunting, scavenging, and gathering along the edges of the crater and surrounding plains. In more recent history, the Maasai people have lived in the Ngorongoro region for centuries. Pastoralists by tradition, they move cattle through the highlands seasonally, coexisting with wildlife. Their grazing practices shape grasslands without destroying them, and their presence added another layer to the ecosystem. During the colonial period, wildlife protection policies altered this balance. In the mid-20th century, the Ngorongoro Conservation Area was established, separating land use inside and outside the crater. Permanent human settlement within the crater floor was prohibited, though Maasai communities continued to live on the surrounding rim and highlands. Today, Ngorongoro is both protected area and living landscape, a place where conservation, tourism, and human tradition intersect uneasily. Tourism has become a major factor. Thousands of visitors descend into the crater daily via steep access roads cut into the rim. From above, vehicles appear small against the scale of the walls. On the floor, they gather near wildlife sightings, forming temporary clusters around lions or rhinos. This concentration raises challenges. Roads affect soil compaction. Vehicles influence animal behavior. Noise and presence alter predator dynamics. Authorities limit numbers and regulate access, but pressure remains constant. Despite this, the crater remains remarkably resilient. Geologically, Ngorongoro is still changing. Rainfall erodes the inner walls gradually, sending sediment onto the floor. Lake Magadi shifts shape with seasons. Mineral springs alter soil chemistry. Though the caldera appears permanent, it is slowly softening at the edges. The crater's rim also influences climate. Moist air rising from the plains cools as it ascends, causing rain to fall more heavily along the rim than on surrounding lowlands. This creates green highlands above drier savannas, a visible line marking the crater's climatic influence. From the rim, the view is overwhelming. The floor lies far below, a patchwork of greens, browns, and blues. Herds move like patterns across grass. Roads curve gently. The scale is difficult to grasp. It is not landscape one stands in, it is landscape one looks into. Descending into the crater reinforces this sense of enclosure. The walls rise behind you, closing off the outside world. Once inside, the horizon shortens. The sky feels closer. The sense of being inside something, rather than upon it, becomes unmistakable. This containment shapes behavior. Animals rarely flee long distances. Predators patrol known territories. The rhythm of life feels compressed, intensified. Births, hunts, deaths, all occur within sight of one another. Scientifically, Ngorongoro offers rare opportunity to study closed ecosystems. Researchers track population dynamics, disease transmission, predator-prey balance, and vegetation change within defined boundaries. Few places allow such controlled observation at this scale, yet the system is not sealed. Diseases can spread rapidly in confined populations. Drought years test resilience. Climate change threatens rainfall patterns that sustain the crater's productivity. Rising temperatures may alter vegetation, affecting herbivore distributions. These uncertainties make conservation here especially complex. Protecting Ngorongoro is not just about preserving animals, but about preserving processes. Volcanic soils renewing grass, springs feeding wetlands, predators regulating prey. The crater is also a reminder of Earth's ability to create abundance from destruction. What began as catastrophic collapse became one of the richest ecosystems on the continent. The absence of a mountain created a world. At night, the crater changes character. Predators become active. Lions roar, their calls echoing off walls. Hyenas whoop across the plains. The rim fades into darkness, enclosing the sounds within. Stars fill the sky above a space once occupied by a volcano summit. Ngorongoro does not dominate through height like mountains. It dominates through enclosure. It does not rise into the sky. It holds the sky inside it. The crater is not simply a geological feature or wildlife reserve. It is a demonstration of how landforms shape life, how collapse can lead to creation, and how boundaries, natural ones, can sustain balance for extraordinary lengths of time. But, like all natural systems, Ngorongoro is temporary on geological scales. The walls will erode, sediment will accumulate, the basin will slowly fill. Millions of years from now, the crater may no longer be visible. For now, it remains. A world inside a world. A mountain turned inward. A reminder that Earth builds not only upward, but inward. And that sometimes the greatest landscapes are formed not by what stands, but by what fell. Through ice that reached for the sea. On the frozen edge of Antarctica, where land, ice, and ocean meet under conditions unlike anywhere else on Earth, a narrow arm of ice once extended far out into the Ross Sea. It did not rise like a mountain or collapse like a cliff. Instead, it crept forward slowly, silently, year after year, shaped by gravity, cold, and time. This was the Erebus Ice Tongue, one of the most unusual glacial formations ever recorded. A structure made not of stone but of moving ice behaving like a solid coastline. The Erebus Ice Tongue formed as an extension of the Erebus Glacier, which flows from the slopes of Mount Erebus, the southernmost active volcano on Earth. Mount Erebus rises from Ross Island, its summit crowned by a persistent lava lake, even as surrounding temperatures plunge far below freezing. This juxtaposition of fire and ice defines the region, creating geological and climatic contrasts that shape everything nearby. Glaciers behave unlike rivers, yet they are rivers in their own way, flowing not with liquid water, but with solid ice. The Erebus Glacier begins high on the volcanic slopes, where snow accumulates faster than it can melt or sublimate. Over time, the weight of accumulating snow compresses lower layers into ice. Gravity then pulls this ice downslope toward the coast. When most glaciers reach the sea, they form broad ice shelves or calve icebergs regularly. The Erebus Glacier behaved differently. Instead of spreading outward, it flowed through a confined valley and extended into the Ross Sea as a long, narrow projection, a floating slab of ice several kilometers long, but only hundreds of meters wide. This projection became known as the Erebus Ice Tongue. By the early 20th century, the ice tongue extended more than 12 kilometers into the sea. It was thick, rigid, and stable enough to persist for decades. Unlike sea ice, which forms from frozen seawater, the Erebus Ice Tongue consisted of freshwater glacial ice, floating because it was less dense than the ocean beneath it. The tongue's shape was controlled by several forces acting simultaneously. Gravity pulled it forward. Ocean currents pushed against its sides. Tides flexed it gently up and down. Wind sculpted its surface. Yet despite these stresses, the tongue remained intact for remarkably long periods. Its survival depended on balance. As long as ice flowed from the glacier at roughly the same rate as melting and calving at the front, the tongue could persist. When that balance shifted, collapse became inevitable. Early Antarctic explorers were among the first to document the Erebus Ice Tongue. During Robert Falcon Scott's discovery expedition in the early 1900s, the tongue was mapped and photographed. To explorers traveling along the coast, it appeared as a frozen pier reaching into the sea, a stark geometric feature in an otherwise chaotic ice landscape. The tongue influenced sea ice formation around it, ocean currents flowing past. The ice tongue created areas of open water known as polynyas, where warmer water from below prevented surface ice from forming. These polynyas became critical habitats for marine life, including plankton, fish, seals, and penguins. In Antarctica, where life is limited by extreme cold and seasonal darkness, any persistent open water becomes ecologically important. The Erebus Ice Tongue indirectly shaped local ecosystems by altering circulation patterns and ice cover. Beneath the tongue, the ocean remained dark and cold. The underside of the ice provided habitat for specialized microorganisms and algae, adapted to low light. These organisms formed the base of a food web extending upward to larger animals. The ice tongue itself recorded environmental history. Layers within the ice preserved information about snowfall, atmospheric composition, and volcanic activity from Mount Erebus. Ash particles embedded in the ice hinted at past eruptions, linking the glacier's story to the volcano above it. Despite its apparent solidity, the Erebus ice tongue was never permanent. Like all floating ice, it was subject to fracture. Stress cracks formed slowly as the ice flexed with tides and currents. These cracks could remain stable for years before suddenly propagating. In 1990, after decades of relative stability, the Erebus ice tongue collapsed. A massive section broke away, calving into the Ross Sea as a large iceberg. The event occurred without warning to human observers, but it followed long-term weakening driven by ocean forces and internal stress. The collapse dramatically shortened the tongue. Where ice once extended far into the sea, only a truncated remnant remained. The coastline changed instantly. Ocean circulation patterns adjusted. Polynyas shifted. What had existed for generations vanished in a single moment. This event was not an anomaly. It was the expected outcome of a system governed by balance rather than permanence. After the collapse, the Erebus Glacier continued flowing. Over time, a new ice tongue began to form, extending again into the Ross Sea. This cycle, growth, extension, collapse, regrowth, is fundamental to floating ice systems. The tongue is not a fixed landform, but a phase in glacier behavior. Studying the Erebus ice tongue has helped scientists understand how glaciers interact with the ocean. Floating ice tongues act as stabilizers, slowing glacier flow by exerting back pressure. When tongues collapse, glaciers upstream may accelerate, increasing ice loss into the sea. This dynamic is especially relevant in the context of global climate change. While the Erebus region remains among the coldest on Earth, warming ocean temperatures elsewhere have led to rapid ice shelf collapse. The Erebus ice tongue provides a natural laboratory for studying these processes in relative isolation. Antarctica itself is often misunderstood as static and lifeless. In reality, it is dynamic. Ice flows constantly. Coastlines shift. Glaciers advance and retreat. The Erebus ice tongue made this motion visible, a rare example of ice behaving like architecture. From the air, the tongue appeared as a pale ribbon, extending from the glacier, sharply defined against darker water. Its edges were often scalloped, shaped by melting and wave action. Crevasses crossed its surface, marking zones of stress. On the surface, the tongue was harsh and hostile. Winds scoured it relentlessly. Temperatures could drop below -40 degrees Celsius, yet it remained structurally coherent, resisting forces that would shatter weaker ice. The presence of Mount Erebus nearby added further complexity. Heat from the volcano influenced local snow accumulation and ice flow patterns. Volcanic gases occasionally settled on the glacier surface, altering albedo and melt rates slightly. Fire and ice coexisted in uneasy proximity. For researchers working in the region, the ice tongue served as both obstacle and pathway. It could block ship access or provide temporary landing zones. Its collapse posed risks to infrastructure and operations, underscoring the need to understand ice dynamics in polar regions. The Erebus ice tongue also serves as a reminder that natural megastructures are not always made of rock. Ice can behave like land, forming cliffs, valleys, and plateaus. But unlike stone, ice responds quickly to environmental change. Where a limestone arch may last thousands of years before collapse, an ice tongue may persist for decades and then disappear. This difference in timescale makes ice landscapes especially sensitive indicators of change. Today, the Erebus ice tongue exists again in a reduced and evolving form. It continues to grow outward, slowly reclaiming space over the sea. Whether it will reach its former length or collapse sooner depends on forces far beyond human control. In Antarctica, no structure is truly permanent. The continent itself is defined by motion, ice flowing outward from its interior, calving into the ocean, raising global sea levels by imperceptible amounts year after year. The Erebus ice tongue illustrates this motion with clarity. It shows how glaciers connect land to sea, how ice can extend, fracture, and vanish, and how absence can follow presence without ceremony. There are no ruins left behind when an ice tongue collapses, no rubble, no fragments visible from shore. The ice simply becomes water again, indistinguishable from the sea it once floated upon. This impermanence gives the Erebus ice tongue a unique place among natural megastructures. It is not remembered for what remains, but for what repeatedly disappears. It was a bridge of ice, a frozen reach into the ocean, a structure shaped entirely by balance. It did not stand against the sea. It floated upon it, and when that balance shifted, it returned quietly to the water. The Erebus ice tongue reminds us that Earth's largest forms are often temporary, that even in the coldest place on the planet, change is constant, and that some of the most powerful landscapes are those that leave no trace when they are gone. In Antarctica, the land itself is moving, the sea is waiting, and the ice is always on its way somewhere else. Thank you for journeying with us through stone whales, glowing caves, hidden worlds, collapsing ice, and ancient craters shaped by time. If you enjoyed this exploration, please like, share, and subscribe, and let us know where you're watching from and what time it is there. Until next time, unearthed secrets will be waiting beneath the surface,